Alright, today we are going to be talking about collision theory and the Arrhenius equation. So I'm going to do a real quickly go over the notes and go over the expectations for this. We will work a couple of problems, then I will leave you to your homework. Alright, so collision theory. There are three main things that we need to look at as far as answering this question. What things need to happen in order for a reaction to occur? So think about this in terms of what's happening at the particulate level, what's happening at the compound level, molecule level, all of that. First thing that needs to happen is the molecules must collide with each other. The molecules have to interact with each other in order to begin to react. The second thing is when they react with each other, the molecules must have enough energy to overcome the activation energy, which we will write as E subscript A. So if you remember, when you think about a potential energy diagram, you have your reaction A plus B, and then we have to overcome this activation energy in order for the reaction to begin. And so we get this on the end, and we're going to have some sort of activated complex there that's in the transition as the reaction is happening, and then we have our product. And doesn't matter if it's endothermic, exothermic, energy going in, energy going out, we still have to overcome this. So molecules must collide, the molecules must have enough energy to overcome the activation energy in their collisions. And then the last thing is molecules must be in the correct orientation. So they have to be facing the right direction, because if they're colliding and they're not facing the right direction, the connection is not going to be made. So let's look at this in terms of graphing, and we're going to look at a couple of concepts. So what happens with a temperature change, and what happens with addition of a catalyst. All right, so we're going to look at a slightly different kind of energy diagram, one that you may have seen, may not have seen in the past. But so in this energy diagram, we're comparing energy on the x-axis to number of moles on the y-axis. Now, when I drew these two curves, this curve and this curve should be the same height. We're dealing with the same number of molecules in both situations. The only change is in graph A, we have a higher temperature than graph B. So let me see if I can clear this up a little bit better, make this one a little nicer. So we have this curve here, and again, we're dealing with the same number of molecules, and what we're looking at is we have our activation energy right here at 120. And notice that on this one, our activation energy is at 120 as well. So at the higher temperature, in a higher temperature, well, sorry, let me make sure I say this correctly. When we're dealing with temperature, in a reaction where temperature is involved, activation energy stays the same. Activation energy does not move. What moves is the whole curve. So notice as we increase the temperature, the curve shifts to the right. So as we increase the temperature, we have this right shift of the curve, allowing more molecules or more particles are eligible to react. In this case, there's fewer particles, so if we reduce the temperature, the curve shifts to the left, making it fewer of them eligible to react. So that's what happens with temperature. Now, let's look at what happens. Let's look what happens with let's look what happens with the addition or subtraction of a catalyst. So one more statement I want to make before I move on from this one. Increase in temperature, we have more molecules with enough energy to react, or enough energy to overcome the activation energy. All right? Now, so let's look at some different graphs. And in this one, we are dealing with a catalyst. How does the catalyst reflect? How does the catalyst affect the reaction? So in graph A, the top graph, we have an uncatalyzed reaction, so no catalyst present. Notice in this one, the activation energy is right here. So we have the same curve, same number of molecules. Our activation energy is somewhere around here at 140. And then down here on this one, our activation energy ends up being somewhere around 110. So the addition of a catalyst, activation energy is lowered. So the curve doesn't shift this time. It's the activation energy that actually changes. So presence of a catalyst, activation energy changes. In reactions where the temperature is changed, the curve will shift depending on which direction the temperature changed. If the temperature is elevated, the curve is going to shift to the right. If the temperature is decreased, the curve is going to shift to the left. This will allow more or less particles to be able, or molecules to be involved in the reaction. Now, down in the bottom of your notes, we just have some more modern graphs rather than a hand-drawn one. We see the same thing occurring though. So this represents our activation energy of an uncatalyzed reaction. Notice there are only a few molecules able to react. And on this one, activation energy is shifted back, allowing more molecules will react. All right, makes sense? Okay, moving on. Now let's look at different situations where catalysts occur. So the first type of catalyst is a heterogeneous catalyst. What this is basically meaning is the catalyst is in a different state of matter than the reactants. And so in this particular case, you're looking at a solid catalyst with a gaseous reactant involved. So most of the time with a heterogeneous catalyst, you're going to have gaseous reactants being absorbed on the surface of a solid catalyst. What the catalyst really does is, if you notice, as the molecule's coming in, it hits the surface of this, and the catalyst actually causes the molecule to be in the right orientation. It turns the molecule so it's in the correct orientation to pick up this new particle and change the molecule. So throughout this, we see a change in the molecule from A to B. And so the catalyst, again, just facilitates this ability of orienting the molecule in the right direction so that the reaction can occur. So remember, the three main things. Molecules must collide. They must collide with enough energy to overcome the activation energy, and they must collide in the right orientation. So they have to be facing the right direction and all of those things. All right, so let's look at one more heterogeneous catalyst. And again, this is the same thing, just a different situation with different molecules. So you have this hydrocarbon coming in that collides with the surface. And when it collides with the surface, it picks up a few more hydrogens on it and then is able to, it's oriented in the right direction. The new particles are attached to it, and then it's released and sent on its way. These are things that are parts of air scrubbers, the catalytic converter on your car, and scrubbers for smokestacks as you're producing different fossil fuels and all of that, so that we don't pollute as much when we're pumping the gas back or sending the waste gas back into the atmosphere. All right, moving forward. So the next type of catalyst that we see is what's called a homogeneous catalyst, and one of the main areas that we see this in is in biology when you talk about enzymes. In a homogeneous, if you remember the term homo, it means same. So in this case, they are in the same phase. So if you have a liquid reactants, you're going to have a liquid catalyst. If you have a gaseous reactants, you're going to have a gaseous catalyst. If you have solid reactants, it'll be a solid catalyst. So looking at this, enzymes are nature's catalysts, cause the reaction to happen faster, more efficiently, whatever. So we have this molecule in here, and I don't care substrate and all of that, but we have our enzyme right here. And the enzyme is going to facilitate the reaction that we want to occur. So the substrate or the compound comes in and it fits into this enzyme. The enzyme is specifically shaped to orient the molecule in the right direction for the reaction to occur. So it comes in, it causes the reaction to start occurring, so it fits in there like a lock and key. It has to be the right shape, it has to be in the right direction to fit in there. Once it gets in there, then the enzyme or the catalyst allows the reaction to occur. And so we see this change from this one complex molecule, and it splits it up into smaller parts, or it changes the shape of it overall. And once that's happened, it releases and it goes about its way, and the body uses it for another thing, or wherever this reaction is occurring. If it would be in the lab, we add that liquid enzyme, and it allows the reaction to occur a little bit faster by lowering the activation energy. All right, so that's kind of collision theory in a nutshell. Now let's talk about calculating activation energy using the Arrhenius equation. So again, we are used to seeing these potential energy diagrams, and in potential energy diagram we can see what the activation energy is based off of that. But if you don't have this, there's other ways that we can calculate it. But we know that we start off with our reactants. It overcomes activation energy. We have our activated complex, and then ultimately we end up with our products. The difference between the reactants to the products is the amount of energy you know, the energy that's present in these compounds versus these compounds. And in here, we have to get over this hump to begin breaking it down, allow it to happen, and go downhill from there. So just real quick review the statements of collision theory. Collision theory says that for a reaction to happen, two things must occur. I split them up into three, but the reactants, to react, molecules must collide with sufficient energy to react. They must collide with enough kinetic energy to cause them to reach the activation energy barrier. So they have to be able to reach activation energy. And then the second thing, molecules must collide with the appropriate orientation for the reaction to occur. They have to be facing the right direction. So when you look at these two factors, in a single temperature, the Arrhenius equation is able to be derived. And so what we get is K, which is the rate constant, equals A. A is orientation. And E, A times E, which is the energy of collisions, and then we raise that to the power of EA over RT, activation energy over RT. Now, things to point out: EA is activation energy, R is the energy constant, which is 8.31 joules, and that's where we get the energy, joules per mole K. So I'll rewrite that. 8.31 joules per mole times Kelvin. All right. So joule molk, or rather than using the lattimulk like we use in gas pressure. Now again, remember those numbers are directly related. It just has to be with what units are we using. Are we using joules or are we using mole K? All right, so A is the Arrhenius constant that tells us how many collisions have the appropriate orientation. Two simple atoms that can collide in any orientation will have a high A value, while two very complex molecules that must collide in a very specific way will have a very small A value. Now, when we're doing these calculations, we don't want to have to deal with particle orientation. That's not for us to count or figure out in our time. So what we're going to do is linearize the equation, and by doing that, we can look at two different temperatures and two different rates, two different Ks, and we can actually eliminate the A in this equation. The A will cancel out. So let's look at, this is the linearized equation. So this is the Arrhenius equation that we are going to be using, which is the natural log of K1 over K2 equals activation energy over R, same R, times 1 over temperature 2 minus temperature 1, 1 over temperature 1. And again, we are going to be using the energy, the ideal energy constant, not gas constant, where we're using joules over mole K. So now, when you look at this as far as linearizing it, what we see is we do have our Y here. The EA represents our M. 1 over T2 minus 1 over T1 represents our X. And then our plus B is actually plus the A that cancels out. All right. So the A gets rid of itself in this equation, and that allows us to have a linear setup, and ultimately that means that we could potentially graph this. On the x-axis you would have 1 over T, And on the y-axis, you would have ln of k. Do it like that so we can tell it's not ink. And so you would get the graph. And from this graph, one of the things that we would realize is M is equal to activation energy over R. And so that means that to solve for activation energy equals M times, let me write that a better way, M times R. All right, so let's work some of these problems. So at 300 degrees Celsius, the rate constant for the reaction of cyclopropane, decomposition of cyclopropane, is 2.41. It's 2.41 times 10 to the negative 10 seconds to the negative 1. At 400 degrees Celsius, the rate constant changes to 1.16 times 10 to the negative 6 seconds to the negative 1. So they want us to calculate the activation energy. So we want to know EA. So again, our equation is ln of K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. Now, the hardest part about this one is just making sure that we stay consistent with what our 1s and 2s are. So this and this are related, and so this is, we're going to call this one 1, and then 400, now let me change colors. So change colors, so 400 degrees and 1.16 times 10 to the negative 6, we will call our 2. So this is our K1 and T1. This is our K2 and T2. So let's go ahead, plug this into the equation, or plug these numbers into the equation. So we're going to take the natural log of 2.41 times 10 to the negative 10, 1 over seconds, divided by, see, I already messed up, divided by our K2, which is 1.16 times 10 to the negative 6, 1 over seconds, equals EA, which is what we're solving for, over R, which is 8.31 joules per mole K, times 1 over T2. Now, notice that our energy is in Kelvin, so we need to convert that to Kelvin. 400 plus 273 is 673, so it's 673 Kelvin, minus 1 over T1. 300 plus 273 is 573 Kelvin. All right, so in this equation, Kelvin is going to end up canceling out, and 1 over seconds is going to end up canceling itself out. So we're going to end up with a unit of joules per mole. And now what we need to do is solve for EA. So in this, it's just simple basic algebra to manipulate and solve for EA. And you end up with, if you don't want to know the answer, pause right here and see what you get first. So pause now. All right, so our answer is going to be 2, and let me erase so I have enough room. 2.72 times 10 to the negative 5 joules per mole. All right, let's look at another problem. All right, so not all of them are going to be so simple that we're solving for EA. This one is relatively easy to manipulate and get to. However, sometimes you will see a problem like this one. So if the activation energy for the decomposition of N2O5 is 1.0 times 10 to the second kilojoules per mole, that's going to be important to look at. Calculate the temperature change. Temperature change necessary to double the rate at room temperature. So we are looking at delta T. So, and then we want to double the rate at room temperature. Room temperature is about 25 degrees Celsius. So that means we have 298 Kelvin. All right. So what we need to do right now is identify K1 is going to be 1, and so we're doubling it, so that means K2 is going to be 2. T1 is what we want to know. Hold on just a moment. Sorry, our T1 is 298, and our T2 is what we want to know. So when we set this up, natural log K1 over K2 equals EA over R. Oh yes, and our EA is 1.0 times 10 to the second kilojoules per mole, but we want this in joules per mole. So we need to convert that, so that makes that 100,000 joules per mole. All right, so plugging it in, and then we have 1 over T2 minus 1 over T1. All right, so sticking everything in the right place. So it's going to be ln of 1/2 equals 100,000 joules per mole over 8.31 joules per mole K. Joules is going to cancel, mole is going to cancel. Units right there would have canceled as well. Times 1 over T2 minus 1 over 298. And now we can do some manipulation. You need to manipulate to where you get T1 by itself. So the first thing I would do is go natural log 1/2 over 100,000 divided by 8.31 we've already gotten rid of our units. So the only unit that we have right now is K. Equals one over T2 minus 1 over T1, which was 298. 298. Now the next step again would be simply moving this to the other side, so natural log 1/2 over 100,000, 8.31 plus 1 over 298 equals 1 over T2. Alright, so at this point, when you do your math over here, that gets you 1 over T2. You take the reciprocal, so T2 should be, and if you don't want to know the answer at this point, pause the video, do your math, and so pause now, and then I'll come back in a moment and tell you the answer. All right, so your answer is going to be 303, actually technically it's 303.2 Kelvin. You can just leave it at 303, but it's 303.2 Kelvin is temperature 2. Now the question was asking for delta T, the change in temperature. So remember, delta T is T2 minus T1, or final temperature minus initial temperature. So delta T is equal to 303.2 minus 298, and that gives us a delta T of 5.2 units Kelvin. All right, that is it for collision theory and Arrhenius equation. Make sure when you watch this, if you missed something, I know I went kind of fast, just go back, rewind the video, watch it again, and you may need to come back to this video during the test or something like that. Remember, this test is going to be a take-home test that you're doing over the Thanksgiving break. Thank you.